Okay, so I guess we can start. ARV, can you please confirm whether am I audible or not? Thank you. And my slides are also visible, right? Great. So let's start with our session today. Our recording is on, and yeah, we can continue. So yeah, good evening all. Welcome to the today's session of NOC 25 CE30 Foundation Engineering NPTEL session. This is a session meant for interacting with our learners from NPTEL courses, and myself Rituraj Singh Sujawat. I am currently working as a Prime Minister Research Fellow in Department of Earthquake Engineering from IIT Roorkee. I am currently acting as an additional teaching assistant for Professor Dilip Kumar Bedia, who is head and professor in Department of Civil Engineering from IIT Kharagpur. So those who are joining these sessions for the first time, let me tell you, these sessions are particularly meant to interact with the learners of our course, and here we will be discussing some of the important concepts required to solve the assignment problems. We will be solving some of the sample questions related to the particular topic which has been covered in that specific week. We'll also be solving some of the doubts other than your sample questions. If you have any technical doubt, feel free to discuss about that. And also, other than your technical query, if you have any other sort of query related to the course, so let's say in general, we are here to discuss about that. And today's sample questions are particularly meant for discussing the questions which are aligning with the analyzing the bearing capacity of the shallow foundations, and how the different theories have been utilized to understand the bearing capacity specifically to the shallow foundation. So before starting that, if you have any doubt concerning with the previous week session, please feel free to ask.
Good evening, sir.
Yeah, good evening here.
It is not a doubt, sir. Actually, last video when you upload,
Yeah, yeah.
your part of audio is not coming.
Is it?
Yes, sir. Yes, sir. I have seen it once. I have seen yesterday.
Okay,
Audience interaction was video and audio. Everything is clear.
okay. My
But
voice was not coming
yeah,
over there.
your voice is not coming. Only lip movement and everything is coming.
So I guess my recorder is might not be recording my audio. Let me check.
Yes, sir. That's what I
Uh,
want to tell you before.
yeah, yeah. Thank you so much for that.
Welcome, sir.
Audio, mic, headset. Okay, I guess now it will be audible.
Any mistakes, sir? You have done last session?
Yeah, I guess the actually I'm using some recording platform to
Okay.
record my audio. So though my audio is audible to the learners, but that particular recorder option is not tracking my voice. So that could
Okay.
have been the problem. But I have
Good.
corrected that now. I
Okay, sir.
don't. I think that won't be problem in future. Yeah.
Fine, sir. Thank you.
Okay. Okay. So then let's move to our today's sample questions. So this is the question number one. So a soil mass has a very low allowable bearing capacity. So you are having a very soft ground which is having a low allowable bearing capacity. A foundation need to be provided for a structure carrying a very heavy load. In that particular case, you need to select the most suitable foundation for the structure from these following four options. Yeah, so the answer for question number one, let's check with that. So yeah, we are having the raft foundation. So generally in the cases, let's assume that you are having a very heavy load coming from the superstructure and your soil is very soft such that none of the foundation option mentioned in the option, let's say strap footing, continuous footing or combined spread foundation, so these type of foundations are not suitable to transfer the load at a shallow depth or even at the shallow depth. So in that particular case, instead of going the for the some specific foundation type like the discrete foundation in your soil domain, we usually cover the whole excavation with the RCC, or let's say uh, any grade of concrete which have been designed to resist that particular load. So we cover the whole excavation with that particular concrete, and we call that particular foundation as the raft foundation. So that particular, so instead of distributing the load among the discrete foundation, you are basically transferring the whole load coming from the superstructure to a raft, and then that raft will basically transfer your load to the soil beneath. So yeah, that was the answer D is the raft foundation for question number 1. Moving to the question number 2. So bearing capacity of soil strata which is supporting a footing size of 3 meter by 3 meter will not be affected by the presence of the groundwater table if they're located at a depth of, so you need to determine that depth of water table such that above below that it won't affect the bearing capacity of your soil strata. Okay, question number 2D. So yeah, let's wait for 1 2 minutes. In that case, let's say when we'll upload the video, so this will give time to our learners who will watch the video at the later stage. So let's see the answer. So yeah, answer 3 is the 3 meter below the face of the footing. So if you are having the foundation which is having a width of let's say 3 meter, so in that particular case the depth of the soil which is under consideration, below which uh, what water depth is available at whatever height, it won't affect the bearing capacity of the soil, is corresponding to the width of the foundation. So let's see from the load transferring mechanism in that particular case. So let's say this is your ground, and you are having a certain foundation which is there on the surface. This foundation is subjected to certain load, let's say P. So if you see the corresponding plastic zones which will usually form when your foundation is subjected to a upcoming load, so in that particular case uh, your stress diagram will look something like this. So usually this particular depth of your stress diagram is having a total depth of if let's say the width of the footing here is having a width of b, so in that particular case the soil domain which will be subjected to the stress coming from the load above is will also be having a domain up to b. So if the water depth is available, let's say in any this particular range of depth, so in that particular case your bearing capacity will get affected, and below this there won't be any effect from water table. So this was your question number 2, and answer is 3 meter below the base of the footing. Moving to question number 3. So
Sir, can I have a small
yeah,
clarification
sure, sure.
in the previous question?
Yeah,
Yeah. Here, B stands for actually width of the least lateral dimension, I think.
yeah. So I have drawn the stress diagram in that particular direction only.
Yes, sir. Yes, sir.
Okay.
The meaning of the B in this one is
Mm.
nothing but for different footings we have different values of the B. For example, square footing,
Yeah,
it is B into B.
yeah, yeah. Yes,
For rectangular footing, it is B into L,
yes,
in which we take only B, least lateral dimension.
yes, yes,
Even for strip foundation, it is a B is a least lateral dimension. Another dimension is infinite.
yes,
In case of circular footing, this is I think it is equal to diameter, no, sir?
yes, sir. It's equal to diameter in the case of the circular
Okay,
footing.
so that's my doubt now. In case of circular footing, in books normally they don't mention.
Yes, yes, yes.
The least lateral dimension is a diameter.
Yeah, it's the diameter basically in that particular case. So it's
That's all,
basic.
sir. That's all.
Yeah, it's a least dimension which is under consideration. Like among all the uh, plant dimensions available, we basically take the least dimension among those plant dimensions, and then we'll basically draw the we'll assume that the stresses will happen uh, orthogonal to that particular dimension. That is the idea.
Yes, sir. Clear.
Okay, okay. So let's move to question number 3. Yeah, I guess the answer is already visible in this, but yeah, you can try. So for the ultimate bearing capacity for the circular footing, so there are some correction factor which have been given by the Tarjaki. So how the shape is basically affecting the bearing capacity. So usually the formula which is given by the Tarjaki for the strip footing, or for let's say for the plane strain cases, so in that particular case we are having the bearing capacity in that with given by the Tarjagi in this particular form. But as soon as other than the strip footing, if your shape of the footing get changed, then there you need to induce some correction factor, and the correction factors are given here. So these correction factors then basically takes your bearing capacity into account. So for the circular footing, this correction factor is 1.3. So this is the resistance offered by the cohesion nature of the soil. So you will apply 1.3 correction factor, and then this is the correction factor which is available due to the let's say the unit weight of the soil. So and gamma is that zero point 0.3 is the correction factor which you will give for your circular footing.
And C is for square footing. First one is for strip footing.
First one is for the strip footing.
B is for none of them. It is not applicable, sir.
uh, D is D is for your
No, no, B, sir.
gum.
B. Second one. B answer.
uh,
B
B.
is
mm,
no, sir. It is not applicable for
yeah,
any of
it's
the
it's
footing.
as of now it's not applicable yet.
Yeah, yeah.
Not of matlab, till my knowledge I don't know whether it's applicable
Yes,
or
sir.
not.
Yes, sir. It is not. We have only four footings usually we measure:
Hmm, hmm,
a strip footing,
hmm.
square,
Hmm, hmm.
circular, and rectangle.
Yeah, yeah.
Rectangular, you have not given any of the option,
uh,
but B option is not belonging to any of the footing.
yeah, B is not available, and for the circular footing, this is, I guess, D is the option. These are the correction factor
Yes, D
which you
option
need
is
to apply. Yeah. Okay.
correct. Here a small comment for you, sir.
Yeah.
Actually, Professor Dilip Kumar Vaidya sir, he solved in second session of week 3.
Okay.
In week 3, second lecture, he solved some 3 examples in
Okay.
which he made a mistake in factor.
In the correction factor.
Yeah, in the example, he has not considered the square footing shape factor. He
Okay.
solved 2 examples of the square footing.
Okay.
For both of them, he has taken 1.3 at the beginning, but
Okay.
last term he has taken 1 by 2.
Okay.
I have made a comment actually in the forum, therefore please go through and you can inform
Yeah, yeah,
the
sure.
videos to
So,
update.
anyhow, if you have mentioned in the forum, they'll uh, pass your query to the TAs,
Other team, sir, it
the
is not.
internal TAs of the Professor Bedia, and I guess those TAs will communicate your query to the Professor Bedia. So definitely,
Okay, sir, done.
it
Then
will be
fine.
considered. Yeah. Okay.
Hmm.
So let's move to our next question. Question number 4. So you need to analyze in Tarjagi's bearing capacity analysis the soil wedge which is just below the footing remains in the state of, so among these four options you need to analyze considering the Tarjagi bearing capacity analysis in which particular state your soil wedge basically behaves, or in which particular, let's say, equilibrium stage your soil wedge will be under consideration when uh, your footing has been placed above the soil as per the Tarjagi bearing capacity analysis.
Sir, all the questions you are giving answer, or this question also it has come by mistake.
I guess it has come by mistake. Let me check.
Check it, and you can update, sir. Once again, no
Yeah,
problem. We'll
yeah,
wait for.
yeah, yeah. Thank you. Animations. CPU. Yeah, I guess all are fine. This two, three questions in between got disturbed. Yeah. Yeah. So Mm, I guess the answer is already clear to you. So it's basically the elastic equilibrium. Uh, so this is the case. So usually, okay, let me explain this thing in detail. So if you are having a certain footing, so the first, as soon as your footing is subjected to some dead load above, so the first action, the soil beneath the foundation uh, will be having your elastic nature. So whatever stresses you are basically applying, external stresses which have been applied to the soil, these stresses can be analyzed using the elastic equilibrium stage, such that you can directly apply the Hooke's law, such that the whatever deformation is happening, if you know the corresponding equivalent stiffness, then you can calculate how much stress which is happening in the soil. Then after elastic equilibrium, your soil basically enters into the plastic stage, and then there are formation of the zones. Yeah, so there are different zone formation which will basically govern whether your soil is in the general shear failure or in the local shear failure or in the punching shear failure. So yeah, the first stage, as soon as the load has been applied to the soil, it will act in the stage of the elastic equilibrium. So yeah, option C is the answer. So let's move to our next question. So yeah, as per Terzaghi equation, you need to calculate the bearing capacity of the stiff footing of unit with which is resting on the cohesive soil. Assume that this particular footing is your surface footing, means this footing is lying on the surface. Those who have joined right now, you can read the question and post your answer in the comment box.
Sir, can you type it the question? Can you retype this question here right now? Possible?
Uh, Please tell me. Do you want me
The
to?
surface footing. Surface footing. Otherwise, once it is recorded, people will be in confusion.
Okay, okay.
That's enough, sir. Surface strip footing. Yeah.
Yeah, your comments have been considered. Thank you so much. Meanwhile, other people can solve this question.
Yes, sir. Go ahead.
Yeah,
Sir, in this question,
hmm.
mm, default, if you don't mention anything, is it we have to assume that it is ultimate bearing capacity?
Yeah.
Because
Assume that
it is not.
you need to assume it's the ultimate bearing capacity.
Yeah.
So whether if you want to calculate the net safe bearing capacity or it's the
Yeah.
safe bearing capacity, it will be mentioned in the
Yeah. For this example, both are same because depth is zero.
yeah, yeah. So
Ultimate and net both are
uh,
same.
you won't be having any effect from the overburden. So
Difference.
it's same. Yeah.
Yes, sir.
So let's understand this. So you are having a certain soil domain available to you. In that particular soil domain, you are having a stiff footing. This stiff footing is resting on a cohesive soil. So this is a purely cohesive soil, which is having cohesion of 15 kPa. Okay. So usually your ultimate bearing capacity is given by, and since it's a surface footing, so uh, your effect from the overburden won't be taken into account. And again, since it's a pure cohesive soil, so you won't be having effect from the friction uh, properties. So frictional, so your unit weight won't be taken into account because it's a pure cohesive soil. So again this will be 0. So the only resistance will be from the cohesive component, and you need to calculate the bearing capacity factor corresponding to cohesion, which is basically the function of your friction angle. Since friction angle is 0 in this particular case, so the ANSI value, if you check the table, is given by 5171. So that's why the QU you can calculate as 5.71 uh, into cohesion is given to you 50. So I guess it's 85.5. Yeah, it's 85.65. So in our option it's closer to 85.5 kb. So option C is your answer. Any doubt in this? If not, so let's move to question number 6. Yeah, so you are having two particular statements in front of you. You need to analyze which of the statement is correct, or like either both of can be correct, or both of them can be wrong. So you need to mark the particular statement. You need to mark the particular option for these two given statements. Just think on this, write the Tarjagi's bearing capacity formula and then understand this, what's basically happening here.
Yes, sir. I think it is only first one is correct.
Yeah, uh, we'll come on this. Let's wait for 3 4 minutes. So you are
True.
saying the first option. Okay, check. Let's check. Okay, so let's check the answer. Yeah, so answer is D, neither one nor two. So just take 1 more minute, just write the bearing capacity formula again and then check where we are going wrong. So let's check this. So usually the bearing capacity for your stiff footing can be analyzed from, right? So let's say for the statement 1, uh, Q and Q. So footing bearing capacity of a footing on clay does not significantly get altered by the presence of the water table. Yeah, so bearing capacity is getting affected by the presence of water table, because accordingly your unit weight will get changed due to the presence of water table. Okay, then
Second term will affect, third term is zero.
yeah,
Because
your
third
third
term,
third term will be 0,
second term will
and
affect.
yeah, your second term will get affected because Q is your gamma df. So
I made a mistake there actually.
yeah,
Uh,
so let's check that. And n statement 2, if you'll go, so saturated clay, so definitely if it's the saturated clay with the phi 0, so your third component of the resistance will get disturbed, so the only components will be remain will be the Q and Q. Now here it's basically talking about the bearing capacity of a footing on a saturated clay is a function of its size. So if we check this particular equation, we can check that the nowhere your size is coming into picture. So usually in the third uh, term you will see the b is available, which is basically taking the size of your footing into account. But let's say for your saturated clay condition, your third term is getting nullified and you will be remain with only the first two terms, which is the c and c and the q and q. So in that particular case, your only bearing capacity formula will be C and C plus Q and Q, and you won't be having any effect from the size of the footing. So the final answer will be neither one nor two. Any doubt in this?
Clear, sir.
Okay, okay. Then let's move to our next question, question number 7.
Here the
So
size means only top, sir. No, three-dimension depth will not come into the picture.
yeah, depth won't come into picture. So
Fine.
anyway, we don't take into account the depth of the means the thickness of the foundation usually don't come into play while evaluating the bearing capacity.
Okay, sir.
Okay.
Fine.
So the question of the similar fashion, so you are having the two statements in front of you and then you need to check which of them is correct, and accordingly you need to mark the correct option for that. One is given answer B, one is given answer D. You can write the equation again and let's check which of them is correct.
Sir, small clarity required in the question.
Yeah, please.
Normally, this mistake is there everywhere in textbooks as well as in many coaching centers and etc.
Hmm.
Cohesive soils is normally indication of the C5 soil. Pure clays are a pure clays is only having a C.
Okay.
Granular materials will have only 5.
Yeah.
Therefore, is your question is correct? Cohesive soil or pure clay?
So for this particular question, the purely this is indicating toward the purely cohesive.
In that case, that's why I have given option D, sir. So if it is a pure clay, answer will be different. Cohesive soil, answer will be different.
Yeah, no, so I guess the terminology which is also used by some of the people here is whatever you are saying, like in between the phi soil and the C soil, you are having the C5 soil. So if it's not the C5 soil, then either it will be the phi soil, and since it has been mentioned cohesive soil, so we are taking the C into account. Yeah, so that terminologies are getting varied from researchers to researchers, like place to place. So yeah, but for our particular case, the cohesive soil meant for the purely cohesive soil, or let's say it's the sea soil, so where you don't have any frictional component into account.
That's a little bit difficult, sir. Here the question because
Yeah, let's let's
even you
take
can
it as
check
a
it.
purely cohesive soil for
Okay, pure clays.
yeah, pure clay for your reference.
Okay, in that case, answer will be different. Pure clays, it will be different.
Yeah, so just you can revise your equations and then you can accordingly modify your answer. Yeah.
This is my modified answer. So.
Okay. Let's wait for one more minute and then we'll solve this. So the answer is C. So both of your statements are correct. Let's have a look on this. So usually your ultimate bearing capacity is given by C and C plus Q and Q plus zero point 0.5 gamma B and gamma. Again, since it's the pure cohesive soil as we have discussed, so your this term will get 0 and as we check that this is independent of B, so your QU, so your statement 1 is correct. It's the ultimate bearing capacity of the soil is independent of the foundation width, because due to the nullification of this particular term, your B is also getting nullified. Then let's check the statement 2. So what is given in the statement 2? So it has been written, the water in soil basically affect the shear strength parameter as well as the unit weight. So let's say when we take the shear strength parameter into account, so how do you take the shear strength parameter? So from the shear strength parameter, you know, the it's basically given by the equation C plus sigma dash and tan phi, right? And what is the, so let's say for the in situ condition, this sigma dash n will get affected due to the presence of the water, right? And since it's getting affected due to the presence of the water, so your shear strength parameter will also get affected, and that's why your statement 2 is also correct. So water in soil affect the shear strength as well as the unit weight. So when we'll talk about the unit weight, so this is basically talking about the unit weight which we are basically taking into account for the calculation of the effective stress. So due to the presence of the water table, your unit weight of your particular soil is also getting changed. So due to that particular change in the unit weight, uh, your water is anyhow affecting the unit weight. So that's why both statement 1 and statement 2 are correct, and the correct option is option C, both 1 and 2. Yeah, please, ARA.
Sir, little interaction, sir, as per the question.
Please.
Statement one is okay, I agree,
Hmm.
because after you mentioned that it is a pure clays,
Hmm.
it is a correct answer.
Hmm.
But coming to the statement two, look
Hmm.
at the clearly question, sir. Water in the soil affect the shear strength parameters, not the shear strength. You have given shear strength parameter.
Yeah, those the
Shear
shear
strength
strength,
parameters means not the tau. It is going to be C and phi.
shear strength parameter as well as the.
Yeah. Your question you have mentioned it is not affecting the shear strength and unit weight. You have given shear strength parameter
Hmm.
as well as unit weight. Unit weight is correct answer.
Hmm.
That's why we go for corrections, submerged or gamma effective, everything.
Hmm.
But shear parameters C and phi are not affected by the water. As you told, sigma n is correct,
Hmm.
which consisting of gamma and D. But if you see the bearing capacity equation, in none of the location we have a tau
Hmm.
or capital S.
Hmm.
Therefore, the
So,
second part,
do you think the, like, how do you calculate the cohesion?
sir?
Okay, I understood. Means, yeah, that is a confusion between the shear strength parameter and the shear strength like the shear strength and the shear strength parameters. So, okay, let's
Yes, sir.
talk about the cohesion also. Let's say talk about the C and phi. So, okay, I'll consider your statement. So, rather than focusing on the tau, let's focus on the C and the phi. So, do you think the cohesion will get affected due to the presence of the water table? Like,
Yes, sir. When they're giving a number of examples in the water table,
hmm,
without water table, with water table,
hmm,
in the corrections we take into account only unit weight in both second and third term. First term is independent of the water table because there is no any unit weight. C will not affect,
yeah.
and phi also will not affect.
No, no. So this is, you're basically talking about that term which is coming into the equation.
Yes, sir.
But
Shear parameters, if you ask,
upon shear, so when we are talking about the shear strength parameters, it's basically the C and the phi in our case.
yes, sir.
So when we are talking about the C and the phi in our case, so how do you basically calculate the C?
It depends upon three types of the tests in drain with drainage, without drainage.
Yeah. So the water will affect your test, right? So
Mhm.
water will affect your test. So subsequently, your cohesion will also get affected due to that, right? Your C value will also get affected due to that.
Mm. Maybe I have to further little bit. I have to spend some time on this.
Yeah, just check with this. So okay, I got your first doubt. That is totally acceptable from my end. I thought it's the shear strength we are talking about, but yeah, it's the shear strength parameters. But even those shear strength parameters are also getting affected due to the presence of the water, because whatever test which you are performing to calculate those shear strength parameters, due to the presence of the water table, those shear strength parameters are getting affected.
Yes, sir. Overall, whatever the shear parameters C and phi and gamma all are affecting, that makes a only left hand side to alter shear
Yeah,
strength or shearing resistance.
yeah.
But your question is not about shearing resistance. Your question is about bearing capacity.
In the second statement, it's nowhere the bearing capacity.
Second statement, it is not related to the bearing capacity, sir.
Yeah, it's not related to the bearing capacity. It's the in general statement they are basically discussing about.
Okay.
Yeah.
Okay. I thought you are teaching about bearing capacity unit. It's related to the same. Mhm.
Yeah, so before going to the bearing capacity means these statements in general come. So we need to study the shear strength parameters previously, right? So we have understand the what we say the more Coulomb failure envelope in our previous lectures, right? So
Mhm.
that failure line, like how we are getting, so that has already, like implicitly, that is a part of the bearing capacity. So
Mm.
the second statement not exclusively meant for the bearing capacity, it's different.
Then in that case, the answer has to be modified. My answer, because
Yeah.
shear strength definitely shear strength is going to reduce because of water only.
Yes, yes, yes.
Yeah. Yeah. Okay, sir.
Yeah, so thank you ARV for the discussion. Please feel free
Thank you.
to ask, like if anyone else is having any doubt in this.
Yes, sir. Thank you.
Thank you ARV. Okay, if there is no any doubt, then I think we can move to our next question, question number 8. I guess it's repeated, we have already covered this. Yeah, so let's go to question number 9. So you are having two circular footings with diameter d1 and d2. It's supported on the surface of the cohesive soil. The ratio d1 by d2 is equal to 2.4. If the ultimate load carrying capacity of footing of diameter d1 is 190 kPa, then you need to determine what is the ultimate bearing capacity of the footing diameter d2. So the question based on the similar concept has been like it has came the for the third time. So accordingly you can evaluate what is the ultimate load carrying capacity, ultimate bearing capacity. Yeah, so let's check the answer. It's based on the similar concept which I have discussed previously. So answer is 190. So as you have discussed, uh, for the particular case, and that too when your footing is lying on the surface, and in the case of the corrosive soil, so your bearing capacity is independent of your size of the footing. So let's say in the first case, if you are having diameter of your footing as d1, and in the second case you are having the diameter as d2, so though the size of the footings are getting varied, but ultimately your bearing capacity is independent of your size of the footing. So you will be having the same bearing capacity that was available in the case of the diameter d1, and the bearing capacity will be same in the case of the diameter d2. So that's why the bearing capacity in this particular case will be 190 kPa. So the answer for question 9 is 190 kPa. Any doubt in this?
No, sir. Fine.
Okay, then let's move to our next question. Yeah, so in this particular question, a consistent deposit of a stiff clay supports a strip of wall footing that is 1.5 meter wide and having a and zero point 0.8 meters deep. The soil has an unconfined compressive strength of 142 kPa, which is having a unit weight of 21.8 kN per meter cube. During the investigation of subsurface soil, no groundwater was found within 6 meter depth. So you need to evaluate what is the ultimate bearing capacity of this stiff footing. So you are having a stiff clay available with you with the zero friction angle. It supports a strip of wall footing that is 1.5 meters wide and zero point 0.8 meters deep. Okay, and the soil has an unconfined compressive strength of 142 kPa, unit weight of 21.8 kN per meter cube. There is no groundwater was found within 6 meter depth, and accordingly you need to determine what is the ultimate bearing capacity in terms of kPa.
Sir, excuse me, sir.
Yes, please.
Is it a Terazaghi's theory?
What?
Default? Is it as per Terazaghi theory or default?
Yeah, yeah, it's a Tarjagi theory you are doing.
Okay.
Yeah. So let's wait for 2-3 minutes and then we'll solve this. Meanwhile, other candidates, if you have any doubt, please feel free to ask. Like, you can unmute yourself and you can raise your query. So let's check this. So whenever you encounter such type of question, 1 second, guys. Yeah. So the correct answer is option B. So yeah, while I was talking, so whenever you encounter such type of question, your first, like, since you need to calculate the bearing capacity using the Tarjagi's theory, so your first task is to analyze the bearing capacity factor. So we know the bearing capacity is given by QU, C and C, Q and Q, zero point 0.5 gamma, B and gamma, right? So since that has been mentioned, the clay, stiff clay, and your friction angle is 0. So one of your shear strength parameter is 0, and in that particular case, your this term will get nullified. So only bearing capacity will be C and C plus Q and Q. So first you need to calculate this bearing capacity factor, which is NC and NQ. So for phi equals to 0, how much is the NC? Is 5.71, right? And how much is the NQ? I guess it's 1, right? Yeah. So for our case, the bearing capacity, the cohesion which is given to you. So yeah, you haven't given with the cohesion, you have been given with the unconfined compressive strength. So what is the relation between the cohesion and the unconfined compressive strength? It's unconfined compressive strength of 142 kPa. So your undrained shear strength or your cohesion in particular case is basically your uh, unconfined compressive strength by 2, right? So your C will be basically 142 by 2, which is your 71 kPa, right? So that's why your ultimate bearing capacity will be 71 into NC 5.71 plus your Q. How much will be your Q? So water table you won't be taking into account because the width of the foundation is 1.5 meter, and your water table is basically available at a depth which is greater than 1.5 meter. Here it has been mentioned up to 6 meter no water table is available. So again you will be taking the unit weight which is given in the question, 21.8 kilometer per meter cube. So 21.8, and your depth of the foundation is given as 0.8. So this will be your Q, and then your NQ will be 1. So I guess how much it's giving, 71 to 5.71 plus 21.8 into zero point 0.8. Yeah, so that is giving you as 422.85 kPa. So this is your bearing capacity in this particular case. Any doubt in this? Yeah, if not so, then let's move to our next question. So yeah, question number 11 is there in front of you. So at 1.5 meter below the surface, located a stiff footing with a width of 2 meter, a consistent medium dense sand deposit makes up the subsurface. The saturated and the dry unit weights of the soil are given to you, which is 21.22 and 18.1. The angle of internal friction is given to you. You need to evaluate the ultimate bearing capacity of the footing when the water table is 1.6 meters below the ground surface. Okay, and given for phi is equals to 34 degree and c is equals to 52.64, and q is given you as 36.5, and n gamma is 38.04, and unit weight of the water is 9.81 kilometer per meter. So here till now we were not taking the water table into account, but now the water table has come into picture. So you need to take the effect of the water table because the width of the footing is 2 meter, and your water table is just available at 1.6 meter below the ground surface. How much answer you are getting? 1075.428. Yeah. So it's not there in the option, right? Yeah, so actually this question has been prepared by the NPTEL team, so even I have checked the calculation. I think it's not giving the required option. So yeah, ARV, can you please like narrate like how did you proceed with the question?
Yes, sir. The equation,
Yeah,
the
let me do it.
write the
So
equation, sir. I will tell the
so
numericals.
so QU is equals to C
0.
and C plus Q and
Okay.
Q plus zero point 0.5 gamma B and gamma, right?
Fine, sir.
In this
First part is
particular
0.
is getting 0 because it's
0.
your
Hmm.
this part. Then only term you will be remaining as Q and Q plus zero point 0.5 gamma B and gamma. Let's understand with the diagram.
Yeah,
So
diagram importance.
so this is a particular case. So this is, let's assume this is your ground level. This is your footing. So your depth of the footing which is given to you is 1.5 meter, 1.5, right? And your width of the footing which is given to you is 2 meter, right? Then your water table is 1.5, 1.6 meter below the ground surface. So here is your water table, right? So this is the depth of 1.6 meter. So total difference between depth from water table to here is 1.1 meter. Okay, now you need to evaluate Q and Q plus zero point 0.5 gamma B and gamma. So Q is basically your overburden which is available at this particular depth, right? So okay, again how much is your phi? So phi is 34 degree and your n q and n gamma is given to you, right?
Given, sir.
So
In
q is basically
gamma
your,
dry into depth of the foundation.
yeah, so gamma dry is how much? 18.1 into depth of the foundation is
One and a
1.5,
half meter.
right? And
Yes, sir.
your nq value is given to you is 36.50.
Yeah,
Okay,
that's correct. Yeah.
and now this bearing capacity is zero point 0.5. And how much is your gamma? Gamma,
Uh,
now there are
gamma
two depth which you have to consider, zero point 0.5. So gamma b and gamma. So how,
gamma effective we have to calculate separately, sir.
yeah, gamma effective we need to calculate, right? Okay, so gamma,
You
one
would
second.
extend the diagram, sir. Diagram you can extend by drawing the remote water table line at 2 meters deep below the foundation.
Yeah, I'll do that. One second, there's some issue with my stylus.
Yes, sir.
Key. Okay, so let's assume that here is your water table and here is your water table. Okay,
Sure.
so
Share the screen, sir.
okay, sorry. Now let's calculate how much is your gamma effective.
Gamma effective is very low value. It is 2.22.
So how did you calculate this? Like let's assume you have considered this
Yeah,
unit weight. So gamma dry,
gamma dry into zero point 0.1
huh, gamma dry into zero point 0.1 plus
plus gamma submerged into 1.9.
21 okay, gamma submerged is 21.2 minus 9.81, right?
Yes, sir. Into
Into this depth
what?
you have considered, right?
2
1.5.
minus of zero point 0.1.
So
1.9 meter.
b minus df you have considered, is it?
Yes, sir. Yes, sir. B minus zero point 0.1. That is indirectly.
Okay, so it's basically the unit weight which is available, and we will multiply with this particular depth, and
You need to draw one more line, sir, at the bottom below the water table. Remote water table line at a
uh,
depth of B.
yeah, okay. So
Draw one more line. Yeah, somewhere below the water table, somewhere you draw the line.
so
Now,
this is your
now,
b, right?
yeah, that is 2 meter. That is 2 meter. That's equivalent to B.
Yeah, so that is 2
Now,
m. Okay, now we can calculate this.
yeah, now it is clear, I think. Now the depth is equal to outside
Yeah, so
1.9 meter.
21.2 minus 9.81, and now your 2 minus zero point 0.1, right?
Yes, sir. Sure. Divided by
Your this depth you will take zero point 0.1, right? Zero point 0.1
zero point 0.1
plus
plus.
2 minus zero point 0.1, right?
Yes, sir.
So
That's correct.
this is your effective unit weight. So how much it is?
2.22.
2.22 kilonewton per meter cube. So it will be again zero point 0.5. So this will be gamma. So 0.5, 2.2 gamma b. And how much is the b? Is b. And how much is the n gamma?
In
Uh,
gamma is 38.04.
how much?
38.04. It is given, sir.
Yeah.
There it is 38.04.
ARB, like I just want to confirm. I think this unit weight, is it getting multiplied with the depth? Means
Yes, sir. It is a weight value of the gamma effective. Gamma 1 into H1 plus gamma 2 into H2 by H1 plus H2.
yeah, but in our case 18.1 is the gamma dry into
We
point
got the
5.
low value because
Yeah, yeah, yeah. Please continue. Yeah, point 0.5 gamma b and gamma. So how much you are getting this value?
I have written in chart box 1075 point.
107 1075.428. So this is your bearing capacity which is available at this particular depth. Yeah, so for water table cases, whenever you are having the water table, so there will be basically two cases. So when sometimes your water table will be available at a certain depth between your depth of the foundation and the ground level, or it will be available somewhere between your base of the footing and b times, or the it is below the depth which is equivalent to b below the base of the footing. So accordingly you need to interpolate your unit weight, and then you can apply your unit weight and you can evaluate your bearing capacity. uh, Thank you IRB for assisting me in this. I think
Thank you, sir.
I've
But it looks a small,
the effect.
small error in the gamma effective calculation, not the 2.22.
How much it is?
It is 11.72.
11.72.
Yeah, yes. Sorry for that. I will once again confirm. 1 minute, sir.
Yeah, even I check. Don't worry.
Because
18.01
it cannot be less than any one of the unit weight.
plus 21.2 minus 9.81 into 2 minus zero point 0.1, answer divided by zero point 0.1 plus
Yes, sir.
2
It is
minus
11.72.
yeah,
11.72
it's
it is.
11.73 something like this. Yeah.
Yes, sir. Now I will finish the remaining answer. I will give you a correct answer now.
So 11.73 will be here. So let's calculate this. 18.1 into 1.5 into 36.5.
Total answer is matching now with one of the option given.
Okay.
Sorry for all these inconveniences.
No, no, it's fine.
Uh,
Even like
it is
the
it's matching with the option A, sir.
option A, right?
1437
Yeah,
answer
even
is
I'm getting
coming.
1437.1842.
So
So yeah,
option A is correct answer.
option A is the answer.
Sorry for
No,
troubling,
no,
sir.
it's fine. So you
Only
don't need.
calculation mistake I did. Otherwise, everything I did correctly.
Mm-hmm. Okay, yeah, and rest of the things are fine. So we
Every,
understood the concept. So basically, whenever you are having the water table, so
hmm.
the only component which is getting affected is your unit weight. So accordingly, you can interpolate your unit weight with whatever depth available to you. So the depth of the water table can basically allows you how to get the effective unit weight. So I guess we can move to our next question.
Yes, sir. Yes.
The answer is A. So yeah, the next question is in the similar fashion. The only part here is now your water table is available 0.6 meter below the ground surface. So now it's the another case where your water table is available between the ground surface and your depth of the footing. So you can take all this particular data from here. The only data which is getting changed is like your water table is available at a depth of zero point 0.6 meter from the ground. So it's somewhere available here.
Can you keep the next slide, sir? We'll see for.
Yeah.
Are you giving time, sir, to solve this?
Yeah, yeah. Please take your
Okay,
time.
okay, okay, okay.
Do you want the data from previous slide?
I have, sir. I have already. Out of I don't know about other people.
Yeah. I think only you are here in the. So other people, I think they left or I think they may rejoin. But
I will
like,
take only depth of the foundation water table zero point 0.6 meters.
yeah, zero point 0.6 meter below the ground.
Okay, sir.
Yeah.
I will know.
So how much is the answer? B you are getting, right?
Same answer. B answer, sir. 12,
So let's,
1200.
yeah,
Exactly is coming.
so this is the answer. Let's check. So QU is your C and C plus Q and Q plus zero point 0.5 gamma B and gamma, right?
Yes, sir.
Let's draw a diagram. So you are having a footing available with you. This is your ground level. Not again. Yeah, so this is the case. So this is, sorry, so the total depth from here to here is given to you is how much?
1.5 meters.
1.5 meter, right? And now your water table is available at this particular depth, uh, which is your zero point 0.6 meter below the ground surface. So this is your water table, right? Now, so the gamma dry unit weight,
Gamma
it's 18.1 kilometer per meter cube, and below this
submerged.
you need to take submerged into account. And how much is your saturated? 21.2 minus 9.81, right?
Yes, sir. It is 11.39.
So for zero point 0.9 meter it's 11.39, right?
Submerged unit.
Yeah, so your QU will be, now this will be 0, your Q will be zero point 0.6 into 18.1 plus zero point 0.9 into 11.39. Your NQ value is how much? 36.5. Your zero point 0.5. Now this
Sir,
will,
gamma effective divided by depth you have not written.
where,
This docket you have written na, zero point 0.6 into 18.1
uh,
plus zero point 0.9 into 11.39 divided by H1 plus H2. 1.5 you have to write.
no, here we won't take the effective, right?
Yes, sir, it is effective only. Whenever it is going to be intermediate, it is going to be effective. Otherwise, you don't get, you can check the answer. Like a previous, we take a effective only whenever the water table is intermediate between ground level and foundation level.
Yeah,
For the second case,
uh,
for example, third term is there na, zero point 0.5 into gamma into B into N gamma.
hmm.
That gamma we take completely submerged.
This is submerged, but here we
Yeah.
are talking about, this is the overburden, right?
Yeah, that is gamma effective, sir, because it's a partially gamma dry. It's a
Okay,
weight value you have to take. Gamma effective you have to take there. Check
so
it, sir.
you are saying we need to divide it by the total
Yeah,
depth.
H 1.5.
Okay.
It is the formula is going to be gamma 1 H1 plus gamma 2 into H2 by H1 plus H2. That's a normally gamma effective.
Okay, let's check that.
Yes, sir, it's correct only.
zero point 0.5, then gamma submerged is how much?
11.33
33 into n
the
gamma,
width
right?
of the footing, 2 meters.
Into 38.04, right?
Yes, sir. 48.04.
zero point 0.6 into 18.1 plus zero point 0.9 into 11.39, answer into 36.50 plus 0.5, 11.33, 2 into 38.04, 0.6 into 18.1 plus zero point 0.9 into 11.39, answer into 36.50. Can you please check it, ARV, once again? I think this
Yeah,
might be.
I have done it, sir. That's correct only, sir. That's correct only. There is something error further is there. What you have written is, can you write, sir? Rewrite once again that divided by 1.5.
One second, I'm checking my calculation again.
Yes, sir. But why you are not getting answer is
No,
after gamma effect.
I'm getting the answer.
Uh-huh.
Yeah, you.
But where is the depth you have written here? Depth you have not written. Na? Gamma effect 2. Afterwards, you have to get the depth 1.5 meter.
Okay.
That is missing.
No, so this is the depth, right?
This is not a depth, sir.
No, so
Actually.
this point
Okay,
0.6
okay,
into
okay.
18.1, point 9 into
You.
11.39. So this is
Hmm.
basically your overburden which we are taking into account. This overburden now will be getting multiplied with your NQ. So this Q is always your overburden. So
Yeah, understood, understood.
yeah,
But
so
you have not considered gamma effective here.
yeah, so okay, you are also correct, I am also correct. So in
Uh-huh.
particular your case, you have considered the gamma effective and then you have multiplied with the whole length and divided by whole length. I haven't gone
Okay.
with the concept of the gamma effective. I
Mm-hmm.
first calculated the overburden for this particular depth, then I have calculated the overburden for this particular depth. I have summed
Mm.
those overburden, then I have multiplied with the bearing capacity factor and Q. So
Okay.
even this approach we can go for.
Yes, sir. Yes, sir.
Yeah.
Then you are
So
not getting still answer?
no, I am getting. Now I am
Getting,
getting it.
sir.
Yeah, it's 1203.8
That's
kilonewton.
all. Sir. That's all.
Yeah, that's why means
Yeah,
because
yeah.
even we can go with the your
This option.
effective approach, or we can either calculate the overburden separately and then we can take the bearing capacity into account.
Okay, okay. Mm-hmm.
Okay.
Yes, sir. Understood. I will
Okay.
try this option, whatever you have done it,
Yeah,
without
yeah,
gamma effect too.
yeah, yeah.
For the previous case, I will try once again and I will recheck.
Yeah, if you check the previous textbook, you can see like there are two, three approaches which you can apply.
Okay, okay. This
Yeah, this
approach I didn't go through till now. I
yeah,
will
yeah.
try this also.
Okay, okay, it's fine. No issue.
Done, sir.
Then let's go for next question, question number 13.
Sure, sir.
So yeah, here you need to identify what is the definition of the sensitivity. So sensitivity of soil can be defined as. So yeah, it's by virtue of its definition we know it's like it's the ratio of the unconfined compressive strength of undisturbed soil to that of soil in remolded state. So whenever we want to know like how much any particular soil is sensitive to the load coming from the superstructure, so we can usually go for the sensitivity test, and in that particular case first we'll apply analyze how much is the compressive strength, unconfined compressive strength in when your soil is undisturbed, and then we'll consider a particular case when your soil is remolded, and then we take the ratio of that, and I think you can go through the codal guidelines. I don't remember the particular code right now, but in that particular case it's given like how you can analyze the sensitivity, and then this is a particular relation you can utilize to calculate the sensitivity of the soil. So I guess it's clear from its definition. Let's go to question number 14. So a sample of saturated cohesionless soil tested in a drain triaxial compression test showed an angle of internal friction 30 degree. The deviatoric stress at failure for the sample when it is tested with a confining pressure of 200 kPa. So you have performed a drain triaxial compression test, and it basically shows an internal friction angle of 30 degree. You need to analyze how much is the deviating stress uh, when it is tested with a confining pressure of 200 kPa. Okay, I think we can take this question maybe in upcoming sessions. So this is not related to the bearing capacity. So meanwhile, like I just want to demonstrate a particular video. Usually these are the analytical formulations which have been used by the geotechnical engineers to calculate the bearing capacity. So whatever we have studied over the questions which we have solved, this is the one of the method which we utilize to calculate the bearing capacity from the conventional formulation available. But there's one more correct approach which we usually go for, like it's through the finite element approach. So it basically here we basically utilize the uh, continuum modeling to understand how our soil is getting filled, and with the help of that particular method we draw the load deformation curve, and we understand how our soil is abruptly changing its deformation behavior, and that particular deformation behavior, the capacity available at deformation behavior will basically give how much is the bearing capacity. So quickly, just give me 5 to 10 minutes, I'll show you that.
Are you sharing another screen, sir?
Yeah, yeah, I'm sharing that. So is it visible?
Yes, sir.
Yeah. So this is a particular case, like usually in like today's geotechnical engineer, this is how they basically utilize a continuum modeling approach to understand how to calculate the bearing capacity. So again, I know some of the people are seeing this platform for the first time. Like this is the uh, commercial package like introduced by the Bentley, and like it's under the Bentley right now. Initially, it is the sole entity. This is the Plexus 2D platform. So in this particular approach, we basically utilize the uh, computational computational power to perform the calculation. As we know, the soil is a very complex domain, and to particularly understand its stresses, uh, we discretize the whole soil domain into small elements, and then we basically understand the stress and strain deformations of those particular elements, and then we sum up the stress and strain approach, and then we understand the deformation behavior in the at a global level. So this is a very vague definition I have given for the finite element software. So there is a whole one semester course which is particularly dedicated to this. But yeah, for the time being, just to introduce how this platform works, so I have given you that particular definition. So in this particular case, as we draw the geometry in the AutoCAD, here is the particular geometry available with you. So here we have drawn a soil domain in front of you, and you can assume that we have assigned some soil properties to this particular domain, and this is the way we basically give the soil. So the constraint model which we have taken into account right now is the Moore Coulomb criteria. We have discussed, we have we had a brief discussion about the Moore Coulomb criteria in the last class, and this is some of the parameters which are dedicated to this constitutive model, and we have assigned this constitutive model parameters to this soil domain, and then this is a particular footing we have designed it as a line element, and now we have subjected this certain load to this line element. Then basically this is the meshing you basically perform to discretize your geometry into small elements. Then you go to stage construction, and there are different construction stages you basically take into account. So first you introduce the soil domain, then you introduce your footing, and then you apply load on that. Okay, so all these parameters can be controlled from this model explorer. And okay, I understand, like understanding this thing at such a speed is almost next to impossible, but my basic ideology is to give you an intuition, like at the finite element modeling, how are basically calculating the bearing capacity. So just have a feel of this
Sir,
theater right now.
sorry, sir. Is there is any possibility of zooming the picture?
uh, is it
Not that picture, sir. Actually, the numericals, whatever you are selecting, no, and that is not visible. All small things.
wait,
Okay.
I'll try this. uh,
Yeah,
mm, is it not visible properly?
yeah. Diagram is clear. Blue color and everything is there. Load visible, but
Mm,
only thing on the left hand side you are selecting, no, something
mm.
number
uh,
one and number two.
ARV, like I'll give you, like if the NPTEL team permits, like at the end of this our whole sessions, I'll take a whole one class on the plexus. uh,
Okay,
we'll have a particular proper demonstration on that.
okay,
For
okay.
the time being right now, like I'm just giving you a brief overview,
Introduction,
like
only
how
introduction.
basically it's happening. So
Okay, sir.
have you worked on the plexus before?
No, sir, I didn't. I didn't.
Okay,
Sorry for
okay.
that.
So sorry for that. I'm so sorry for that. So I'll introduce you with the plexus in the last sessions, for sure.
Okay,
Okay.
okay, sir.
So you are having a certain load. Any other finite element software you have worked upon?
No, sir. That's also no. Undergraduate level, we didn't. We don't have.
Okay, 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 okay. You are in industry, right? Like
No, no, no.
in.
I am academician. I completed my master's program also long back.
Okay, 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 okay.
During that time,
Hmm.
we have a faculty member who is giving a FEM, was a retired, just retired when we joined MTech in
Okay,
Government Engineering College.
okay, okay,
Then instead of FEM, I have taken no option, ground improvement, another faculty was there. I have taken that.
okay,
So
okay,
I
okay.
missed the important course.
No, 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 no issue. Like at least at the geotechnical perspective, like I can introduce you, like I can give you a brief overview about these packages, like
Okay,
in
sir.
between
Okay.
the classes,
Yeah.
so we can have a feel out. So this is the thing. So we are basically dividing the construction stages. So now I'll perform the calculation here. So this is the calculations which is happening here. So that's why, like we are not that much thorough with the analytical calculation nowadays, like since we are
Yeah.
solving also, we like I'm making the small mistakes because basically right now we are utilizing this whole finite element packages to solve our geotechnical problems.
Mm.
So again, yeah, I totally understand that to have the proper conceptual theory from the Tarjaki's formulation, it's very important. But since in our practice right now we are more into the finite element packages, so we had a little distance from those formulations, and that's why like we are making some errors in between.
Okay.
Yeah, so our calculations have been performed. I'll share my screen again. 0 40 20. I'll select a node. Yes, Sanjay. Anything? Actually, we are basically calculating the bearing capacity using the finite element approach. So I'm just giving a brief overview right now. Like we'll be uh, having a proper demonstration in the whole session will be dedicated to that. But right now, I just want to give a brief overview how it's happening. So here,
Okay, fine, sir.
okay, Sanjay, thank you. So this is the bearing capacity calculation. So this is how your finite element model will look like. So this is your soil domain, this was your footing, and it was subjected to the load. So due to the load, your whole footing is getting uh, it's going under subsidence, and that's why your soil is also getting deformed. And this is how your finite element deformation would look like. So now let's see how your bearing capacity, like how we'll basically calculate the bearing capacity. So uh, for that particular case, I have selected a node, or I have selected a particular soil element in between the footing, and then we are basically drawing the load deformation curve, and through that load deformation curve, we are basically evaluating the bearing capacity. So we'll go to charts, new. Okay, sorry. Yeah, so this is how your load deformation curves look like. So what's basically happening? So this was your foundation, and as soon as you are applying a load, this is getting deformed. So let's say if I'll take a particular node uh, at this location, which is between the footing. So that particular node, as soon as you're applying the load to that foundation, that node is getting deformed with the time, and this is the load deformation curve which you are getting along the time. So this is the load deformation curve, and as you can see, as soon as you are applying the load, there comes a sudden moment where your footing is not able to take any further load, and your load deformation curve will get changed abruptly. So whatever capacity which is available at this particular node from the soil domain is your ultimate bearing capacity. So through the finite element packages, this is how we evaluate the ultimate bearing capacity. So that was the part I wanted to highlight upon. So in the
If we
finite
take a
element, yeah,
different node, the deflection will be different, sir.
yeah, deflection will be different in that particular case.
So final answer, the node should be always close to the footing.
Yeah, it should be always close to the footing.
Anywhere, at center or edge or anywhere, it doesn't matter, sir.
uh, Usually we take it at the center because
Center,
that is
okay,
the most critical point which will be having. Again,
okay,
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 if you are having, if you'll go through the Tarjagi's approach, so we see usually your plastic zone starts at the edge of your footing.
okay,
So sometimes we also take the node at the edge into account, but we'll check into those particular sessions like how much is your result is getting fluctuated if we take the node at the center or if we take the node at the edge. So
okay,
we'll check that. We'll be having a proper demonstration on that. So that was
okay.
the thing I wanted to highlight upon. If you
Thank
are
you.
having the queries related to finite element, please hold your queries. We'll be having a demonstration on that. If you have your queries related to the NPTEL sample questions which you have done today, please feel free to ask as we can wind up our session today. Please, if you have any query, please raise your query.
Sir, APM, I am zero. I don't have anything because I will learn further.
Yeah, yeah.
Regarding today's entire session,
Mm-hmm.
I have a small clarity required because in the
Yes, please,
terminology of
please,
these
please,
three
please
soils
raise.
which we have, we have a C
Mm-hmm.
soil, Phi soil, and C Phi soil.
Yeah.
Can you exactly tell what is, as per your terminology, what is the name you are giving for all these three soils? C soil, Phi soil, and C Phi soil.
Yeah, in our case also, like practically you also know, even I know ki this pure sea soil and pure pie soil are not possible in the
No
nature,
problem.
in the nature right now.
Yeah.
So
Mhm.
in our nomenclature also we use either sea soil, pie soil or the sea pie soil, and that is
Okay.
getting differentiated on the basis of the friction angle which is available.
Right.
Yeah, so that's the our terminology.
That's all, sir. Then
Okay,
done for today.
okay, okay, Avi, thank you so much. Okay
Thank you,
then.
sir. Thank you very much. Thank you, sir.
Okay.
Thank you very much.
Thank you, Arvi. Thank you, Sanjay.
Bye, sir.
If
Bye,
there's
sir.
no any further query, let's wind up our session today. Thank you so much for the joining, and I'll be posting this video. Those who are watching this video at the later stage through the YouTube, please post your question in the comment sections. I'll be surely addressing your questions there, and you can also raise your questions in the upcoming Tuesday at 6 p.m. Thank you so much.
Thank you, sir.
Thank
Sanjay is asking some links, sir. What is that?
Yeah, so it will be given to you by your the NPTEL team. So there will be one sheet which is shared to you. The link of the sheet will be shared to you. In that particular sheet, you will be having both the YouTube video link as well as the
Oh,
PDF PDF.
these links are available in the problem solving session at the bottom of the week one, week two, week three, week four. All
Yeah,
there was a one small location called problem solving session. If we click that,
yeah.
it leads to the directly all the YouTube videos,
Yes,
problem
yes.
solving sessions.
We can even approach.
Okay.
So
Yes,
you'll be
Okay. Thank
having
you so
through
much.
you'll be having through the let's say the in the announcement of the NPTEL sections, you can basically approach all the content. So you can have that.
yeah. Thank you, sir. Thank you very much.
Okay, guys.
Thank you, sir. Thank you.
Thank you so much.